Okay, good morning. So, we have been discussing about the energy equation in the previous lecture. So, we found that this is our nothing but nth phase or individual phase energy equation. Okay, and in this individual phase energy equation, so this is for particular nth phase. So, this Qn is the heat transfer, Wn is work transfer, and these heat and work transfer are actually with the external surroundings, and then Qin and Win are the internal heat and work transfer of nth phase with other phases present in the control volume. Okay, and delta n into del by del xj uci into sigma cij. This will include two components. One will be flow work and other will be viscous dissipation, and these two will be coming into picture only at the boundaries of the control volume. Okay, and we had made the assumption that at the boundaries of control volume only continuous phase is present. Okay, so that's why this Kronecker delta operator is over here, which will be equal to 1 only when n is equal to c, and this has to be equal to rate of change of total specific energy within the control volume and any outflow of energy across the boundaries of the control volume. So En star over here is nothing but total specific energy, which is equal to internal energy plus kinetic energy plus potential energy, and internal energy is given by a symbol En. Now, we know that if I write down this equation, nth phase equation for all the phases present in our system, and if I take their summation, then I will be getting summation of Qin. So, summation of Qin over the n number of phases has to be equal to 0, because if one phase is receiving heat, other will be losing heat. So, if for all the phases we take the sum, that will comes out to be 0. Likewise, all the internal work interactions has also to be equal to 0. And epsilon n, we are writing that if there is any other form of energy transfer between the phases within the control volume, which is other than heat and work transfer, that will also be equal to 0. Okay. Now, if I assume that in my system I only have two phases, one dispersed phase and one continuous phase. So in this scenario, what will be happening? Whatever be the QIC, it means heat transfer to continuous phase, that will be nothing but equal to minus of QID. Okay, is this one clear? Because one will be losing the heat, other will be gaining the heat. Likewise, WIC has to be equal to minus of WID, and if I know that FDI is the force which is acting on dispersed phase in ith direction because of the continuous phase, and UDI is the velocity of the dispersed phase particle in ith direction, then multiplication of UDI and FDI will give me nothing but my dispersed phase work interaction. Okay. And likewise, other form of energy interaction, epsilon C has to be equal to minus of epsilon D. Okay. Now, when we are doing this summation, so till now we have discussed only these terms. When I will be doing summation for Q1 and W1, then I will be getting summation of, so capital Q, say overall net heat transfer with external surroundings is equal to summation of N and Q1. So it means the heat transfer, total heat transfer of all the phases with the external surroundings. Okay. Likewise, I can do for W. Now, whenever we are considering the external surroundings, then because external surroundings are not part of our system, so in this case, when I will be taking summation, it will not be equal to 0. Okay, it can be 0 for some special case, but it will not always be equal to 0. Is this one clear? So, if I now do the summation on left hand side, then I will be getting del by del t sum of n rho n alpha n into En star plus del by del xi summation of rho n alpha and u n I into En star. Okay. When I will be doing the summation for this particular term, because this particular term flow work and viscous dissipation, it will be only applicable at the boundaries. So it will be only applicable for a continuous phase. So that's why this term will be coming without any summation size and summation sign, and this delta n operator will also be removed because now we are considering the continuous phase also when we are doing summation over all the phases. Okay. So now what I can do, this on the right hand side, this term is with positive sign. So when I will be bringing it to the left hand side, so del by del xi, it can come with the negative sign, minus ucj into sigma cij. And this will be equal to net heat and work interactions. Okay. So this will be becoming nothing but my combined phase energy equation. Is this one clear? So this is my combined phase energy equation. Now we know that for internal energy, if I make the assumption of ideal gas, then what I can do? We know that for ideal gas, internal energy is equal to Cv into dt. Okay. And if I do integration, then E can be written in terms of Cv into T plus constant. Okay. So if I make this assumption, then I can write that En internal energy can be Cvn into Tn plus constant. Okay. Now what I will be doing, this En star is nothing but En plus Gz. Is this one clear? Now what I will be doing, in this En I will replace it with Cv and T. Okay. So if I do this replacement, ultimately I will be finding that rho n alpha n into Cvn. Okay, here what is Cv? Specific heat at constant volume of nth phase. Okay. So this will be coming outside, and inside it can become del Tn by del T. So please, I am not writing now the combined phase equation. I am writing individual phase energy equation. Okay. So it means I am doing substitution in the equation which is shown in the previous slide. Okay. So there if I do substitution, then it will become del by del T of Tn plus Uni into del by del Xi of Tn. Is this point clear? Plus I will be having some more additional term also, and that additional term is actually written on the right hand side. Okay. So what I will be getting with this? With this I will be getting del rho n alpha n divided by del T, clear? Plus del by del xi into rho n alpha n into uni. Okay. And that entire quantity will become equal to In. Is this point clear? And then with In, I will be having En star minus Uni into Uni. All are clear with this point? So basically, whenever you will be doing the replacement of En, then ultimately one derivative will be for Tn and second derivative will be for all the remaining terms. Whenever you will be taking the second derivative for all the remaining terms, that will give you In times En star minus Uni into Uni. Is this point clear? And here, because I am talking about the nth phase, so delta n into sigma Cij into del UCi divided by del Xj plus Qn plus Wn plus Qin. And how Win is replaced now? What is Win? Internal work interaction. So if I know that force acting on nth phase in ith direction because of all other phases is F and I, and relative velocity between the dispersed phase and nth phase is u di minus u ni. So then force into relative velocity will be my interaction. Is this one clear? So this is now nth phase energy equation, but this nth phase energy equation is in temperature form. Okay. What next? If I write the combined phase energy equation in terms of temperature form, then what I will be doing? Again, I will be doing summation. So in the left hand side, I will be getting summation n, rho n alpha n Cvn into del Tn by dt plus u1i into this. And here, this delta will be dropped, okay, because continuous phase is coming. And this is all these are the nothing but my additional energy interaction terms. Is this one clear? What is this? I need not to explain now. This is nothing but my area averaged energy equation. And this is applicable for nth phase. Okay. So in the second term, we have multiplication and division of area, and then we have all the terms like we have for all other cases. But all the quantities are over here nothing but area averaged quantities. And this is combined phase area averaged energy equation. Okay. Now, if say mathematical form is given, you should be immediately able to tell by just looking into the mathematical form that this is applicable for what type of physical situation. Like, is it for individual phase, is it for combined phase, is it area averaged equation? Okay. So by just looking into the mathematical form, you should be able to give its physical description. Okay. Now one important point. In case of hydrodynamics, we have seen that when a particle is dropped into the flow field, what happens? Particle will try to come in equilibrium with the surrounding phase, okay? And while particle is trying to come in equilibrium with the surrounding phase, it actually takes some time, and that time we call as hydrodynamic relaxation time, okay? Likewise, what will be happening whenever particle is dropped into the continuous phase, this particle can be at temperature other than the temperature of the continuous phase. It can be hot or it can be cold. Okay. So when I will be dropping the particle, ultimately what will happen? It will take some time to come in equilibrium with the surrounding phase, temperature of the surrounding phase. So that is our thermal relaxation time. Okay. So over here we will try to analyze one situation, and this is very specific. So I will consider that I am having spherical particles. So first assumption is what I am considering? Spherical particles. And these spherical particles are suspended in the surrounding gaseous phase. So surrounding phase is gas. Okay. We know that when I have a particle and when I have surrounding gas, there will be energy exchange between the two. Okay. And mostly the energy exchange will be across the surface area of the particle. Okay. Because area will be participating in the energy interaction. Okay. Now energy interaction can be in three ways. One, because of conduction, if I assume that particle is just present in the fluid and velocity of particle and the velocity of surrounding phase are same, in that case, with reference to the surrounding fluid, particle is in stationary position. Okay. So based on that, because there will not be any relative motion between the gaseous phase and the particle, my heat transfer will be because of the conduction. Okay, because bulk motion of fluid is not happening over the particle. So with reference to fluid motion, particle will be acting stationary. So if my particle and fluid are moving at same velocity, sorry, at the moment I am assuming that in case relative motion is not there, then my mode of heat transfer will be conduction. In case the relative motion is present, then heat transfer will be because of convection. So conduction will be coming into picture by default, but plus this fluid motion between the solid and the gaseous mode will also result in heat transfer. And other than that, depending upon the temperature conditions, if the temperature difference between particle and the surrounding gas is very large, then radiative heat transfer may also come into picture. But at the moment we will be considering that radiation in this case is negligible and the heat transfer is only by conduction and convection. Okay. Now, what will happen? If there is relative motion present, then of course the effect of convection has to come into picture, and we know that to account for effect of convection, what we do? We do take the help of Nusselt number for defining the rate of heat transfer. Okay. So what does Nusselt number represents? Fundamentally, Nusselt number is nothing but rate of convection heat transfer divided by conduction heat transfer. Okay. So it typically represents that because of the convection, how much enhancement is there in the heat transfer. Okay. If with reference to the soul conduction effect. So when I am having a spherical particle, I can define the conduction heat transfer for spherical particle as 2 pi r, where r is radius of particle, into k into Tc minus Td. Okay. So basically, what is Tc? Tc is temperature of the continuous phase, Td is temperature of the dispersed phase. Now we will again make some assumptions over here. When I am considering that my surrounding phase is gas and particle can be, if surrounding phase is gas, then for having multiphase flow situation, okay, having multiphase flow situation, particle either has to be solid or it has to be liquid. Is this one clear? So particle either has to be solid or it has to be liquid, because if particle is gas, then it will not be immiscible with the surrounding gaseous phase. So for being it immiscible, it has to be either solid or liquid. Now we know that the thermal conductivity of the solid and liquid is very high in comparison to thermal conductivity of gases. So from here I can say that the particle being solid and liquid, its thermal conductivity will be very large in comparison to thermal conductivity of the surrounding continuous phase. Is this one clear? Now, if any temperature gradient is present within the particle, then there will be heat transfer within the particle also, and then particle will be transferring heat with the surroundings. Okay. So when I am considering that surrounding fluid also stationary, the heat transfer is only taking place because of the conduction, then because thermal conductivity of solid is more and thermal conductivity of surrounding gaseous phase is less, so the rate of heat transfer from the particle to the gas will be controlled by the thermal conductivity of the gaseous phase. Is this one clear? Because it can happen that from inside heat may flow at faster rate, but if outside conductivity is low, the gas will carry heat transfer at the lower rate. Okay. So overall effect of rate of heat transfer from solid to gas will be actually controlled by the thermal conductivity of the surrounding gaseous phase. So that's why when I am writing over K, I have to write over here K. Is this one clear? Another important point is, when I am having this particle, I know that the rate at which surrounding is taking heat is less in comparison to the rate at which heat can flow within the particle. So because of high thermal conductivity of particle and because of its smaller size, we can assume that, or we can consider that, the temperature of dispersed phase is uniform. Is this point clear? See, if the rate of heat transfer in the surrounding is more, then surface of particle will be cooled at the faster rate. So if surface is cooled at the faster rate, then there will be existence of gradient between the core and the surface. But if rate of heat transfer at outside is slow, then the movement outside heat will try to decrease the temperature of the surface. Immediately from the core of the particle, heat will be provided to the surface, okay, because conductivity of inside medium is high. So because of this reason, we will be finding that temperature within the particle there will not be much temperature gradient, and temperature of particle can be considered to be uniform. Is this point clear? So this is our next assumption, and of course we know that this assumption comes into picture only when our Biot number is less than 0.0. Okay, so particles are smaller and they have high thermal conductivity.
This is energy dissipation per unit length.
Yes.
Length will be what?
So over here we are considering it to be the length scale of the particle, because ultimately what will happen, here is your one temperature, and immediately at the surface, because of the presence of dispersed phase, temperature will be equal to continuous phase. Here it will be equal to dispersed phase. So that we are considering as the temperature. Is this one clear? Okay. Now, if this is my conduction heat transfer, what will be convection heat transfer from this? We know that convection heat transfer is equal to Nusselt number into conduction heat transfer. So what I need to do, I need to simply multiply what? Nusselt number over here. Okay, all are clear with this idea? So what I have done, I have multiplied Nusselt number with conduction heat transfer to determine the convection heat transfer from the particle. But one important point, when I am calculating this heat transfer, this is from a single particle. If I am having ND number of particles per unit volume, then total heat transfer from all particles will be heat transfer from single particle multiplied by ND. Is this one clear? And this I can simply call as nothing but the amount of heat added to the dispersed phase by the surrounding continuous phase. So I can call it to be QID. This point is clear. Now, value of Nusselt number for this type of situation can be given by this particular correlation, which is 2 plus 0.6 into RE power 1 by 2 and Prandtl number power 1 by 3. Is this one clear? So Nusselt number you can calculate from this equation. Now, this is the total amount of heat transfer to the particle. What will be total amount of heat transfer to the particle? It will be equal to net rate of change of energy of the particle. All are clear with this point? So energy, if say I am adding heat to you, what will happen? Your temperature will be increasing or your energy content will be increasing. So that is the reason the rate at which heat is added to the particle from the surrounding continuous phase, that will be equal to rate of change of energy of the system, and that is rho d alpha d into CSD, where CS is specific heat of the dispersed phase particle and total rate of change of temperature of the dispersed phase particle. Is this one clear? All are clear with this idea? Yes. Means it is, Nusselt number is not specific to a particular phase, because what is convection? Convection typically takes place in between the two different phases. For example, a solid boundary and a flowing gas over that. Okay. So over here, our particle is acting as the surface and surrounding gas is a fluid which is flowing over that. So for the particle and gaseous combination is this result. Is this one clear? So if I simplify this equation, I will be getting dt d by dt of Nusselt number by 2 into Tc minus Td divided by T. So this is rate of change of total rate of change of temperature with time. Nusselt number is dimensionless. This is temperature. So this has to be have unit of time. Okay. And this particular term is something which is called as thermal relaxation. Is this one clear? Now, if you just simplify this algebraic equation, you will be finding tau T is equal to specific heat of dispersed phase multiplied by density of the dispersed phase into its radius square divided by 3 Kc, where Kc is the thermal conductivity of the surrounding continuous phase. Is this one clear? And why we have taken thermal conductivity of surrounding phase? Because we have assumed the situation that solid or liquid particles are present in the gaseous phase, and gaseous phase is having low thermal conductivity, which is controlling the overall rate of heat transfer. Is this one clear? So this equation is for thermal relaxation time. This can tell you that in how much time, if you drop the particle, then in how much time it will come in thermal equilibrium with the surrounding phase. Okay. All are clear up to this point? So two important time scales we have discussed, hydrodynamic relaxation time and thermal relaxation time. Though you have to keep this into mind, whatever the discussion we have made over here, this is for very specialized cases by considering the spherical shape of particle and making many assumptions. So when cases are generalized, then we cannot use directly these formulas, but we have to derive their variants for the given situation. Okay. Now let us talk about interaction of particles with turbulence. Okay. So typically what will happen when you have a continuous fluid flowing, in that fluid if you add particles, then what will happen? These particles may try to either enhance the turbulence or these may try to decrease the turbulence. Okay. So two major important things happen. If you have a turbulent flow and particle present, then what will happen? The turbulence across the particle will try to create a field of strong shear across it. So because of the strong shear present across the particle, that particle can either break or it can coalesce to form a larger particle. See, situation is, say this is the bubble. Here some turbulent eddy is moving like this, here it is moving like this. What will happen? It will try to break from the center. Okay. If you have situation like this, these two particles are there. So these will try to come together and finally make a bigger particle. So turbulence can lead to breakage and coalescence of the particle, and this breakage and coalescence will be mostly dominant for fluid particles. Say if liquid is present in gaseous medium, then liquid drop can break or liquid drop can coalesce together. Okay, and if similarly if air bubble is present in the surrounding liquid phase, then that bubble can also break or coalesce. But if you have solid particle, then solid particles typically are of rigid nature, so chances of breaking and making are less, unless or until you have very strong forces because of the turbulence which are acting on the particle. In that case there can be slight breakage and distortion of the solid particles. Okay. Second important point is the presence of turbulence and particle can also modify overall turbulence behavior. what it means that if particles are present, then particles can either decrease the turbulence or particles can enhance the turbulence. Okay, so these different situations can happen. So can you tell me, whenever we have turbulence present in the system, then what are the length and time scales with which we can characterize the turbulence? Do you have any idea about? Okay, so whenever we talk about turbulence, say a flow is happening through a pipe. So while the flow is happening through a pipe, if flow is turbulent, I can find turbulent eddies of various sizes, and these are rotating at different velocities. Okay, so typically if I look into, do you understand what is turbulence? So you will be finding in a turbulent flow a large number of rotating small structures. So these are called as turbulent vortices. Okay, so typically when you look into the flow dynamics, you may find that some turbulent eddy may be of very large size close to the diameter of the pipe. Some turbulent eddy may be of very small size, having size, say 1/10 of the diameter of the pipe. You may have some turbulent eddy where the diameter is say 1/4 or 1/5 of the pipe size. So it means that in a turbulent flow, the length scales of turbulent eddies will be completely in the wide spectrum. Moreover, you will also find that some of the turbulent eddies will be rotating at the faster speed, some will be rotating at the slower speed. So their time scales will also be different. Typically, in a turbulent flow, the turbulent eddies which have larger length scales, these carry higher turbulent energy, and which have small length scales, these carry the less turbulent. Okay. The lesser length scale turbulent eddies are typically the ones which receives energy from large turbulent eddies. Is this point clear? So the smaller one receives the energy from the larger, and because the smaller one are receiving energy from the large, so that's why the smaller ones are the ones which can lead to viscous or dissipation of turbulent kinetic energy. Okay, typically the motion of smaller turbulent energies is mainly governed by the energy exchange with the large turbulent eddies. So what these do, these receives the energy from the large turbulent eddies, and that because of that energy these try to rotate. So ultimately these are consuming the energies of the large turbulent eddies. So these are dissipating turbulent energies. And larger turbulent energies are the ones which receives the turbulent energy from mean flow. So even if my localized flow structures are rotating here and there, still you will be finding that overall in this pipe the water will be flowing from left to right, if I assume it to be water or any other fluid. Okay, so it means that though the localized fluid motions are randomly here and there, overall flow is actually taking place from left to right. So overall flow which is taking from left to right, that we call as nothing but our mean flow. And in order to allow the mean flow to happen, we have to supply certain amount of energy. So whatever energy we are supplying, from there actually the larger eddies are receiving the energy of turbulence. Is this point clear? Because the energy you are supplying, where that energy will be invested, that energy will be majorly invested in overcoming the shear stress, wall shear stress. Okay, and across the wall shear stress, the turbulent energies which can grow, these will be of size identical to the pipe length scale. Okay, so that is the reason that majorly in high shear zones the energy is transferred from the from the main flow to the larger turbulent. Is this point clear? Sorry. Yes, yes, that can happen. But ultimately, what happens basically, the smaller eddies typically, if these are not receiving the energies, these die down. So these receive some energy, and after that, these immediately die down. However, their interaction can lead to continuous changes in the length and time scales. Okay. Okay, now as we have understood that in a turbulent flow there can be presence of eddies of different sizes. So if we have to properly resolve the flow, we should be able to determine or properly resolve the turbulent eddy of smallest size. Is this point clear? So smallest length scale which can be present in a turbulent flow, that is called as Kolmogorov length scale. Is this point clear? So as we can have turbulent eddies of different sizes, but whatever be the smallest size of the turbulent eddy, that will be governed by the Kolmogorov length scale. And eddies also have different time scales. I told you that larger eddies moves at the slower speed, but smallest eddies moves at the faster speed. So if we have to properly resolve the turbulent eddy, then we should be able to define the time scale of the fastest moving eddy. Okay, so the time scale of fastest moving eddy is called as Kolmogorov time scale. So this is my Kolmogorov length scale, which is given by nu. Nu is actually kinematic viscosity cube divided by epsilon power 1 by 4. What is epsilon? Epsilon is called as rate of dissipation of turbulent kinetic energy per unit mass. Okay. Rate of dissipation of turbulent kinetic energy per unit mass is something which is called as epsilon. And tau is equal to nu by epsilon power 1 by 2. All are clear with this point? Now, the epsilon can be given as u cube by L. What is u? Reference flow velocity and L is length scale of the flow. So if I take reference flow velocity power 3 divided by length scale of the flow, this ratio is typically nothing but my epsilon, rate of dissipation of turbulent kinetic energy. Now I can use Reynolds number as UL by nu. Okay. So if u is my velocity, L is length scale and nu is the kinematic viscosity, then Reynolds number can be defined like this. If I use this definition over here, then ultimately my lambda by L will be proportional to Reynolds number power minus 3 by 4 and UT by L will be proportional to Reynolds number power minus 1 by 2. All are clear with this idea? So it means that length scale, Kolmogorov length scale is proportional to Reynolds number power minus 3. Now, after this information, let us try to visualize this graph. Okay. So in this particular graph, what we have, along the x-axis I am having ratio of particle diameter to turbulent length scale. So particle size is d divided by LT. What is LT? LT is my turbulent length scale of the turbulent eddies. Okay, and in this side I am having change in turbulent intensity. What does it mean? Turbulent intensity for flow with particles minus turbulent intensity for flow without particles divided by turbulent intensity for flow without particles into 100. Okay, so say if I have some flow of fluid and there is no particle, then corresponding to that whatever is my turbulent intensity, if in the same situation I add some particles and then I if try to determine what will be happening on the turbulent intensity, then our experience or the experimental measurement shows that when the size of particles is very small, okay, so this range you can see here, diameter of the particle divided by turbulent length scale is very small. So when size of particles is very small, then the change in turbulent intensity is in negative side. What it means? It means that the presence of particles has decreased the turbulent intensity. In the moderate range of particle sizes, majority are coming close to 0 and few are coming actually even lesser. So it means in this range also, if presence of particles is there, either the presence of particles will try to decrease the turbulence, or for some cases it will not make any difference. But when my size of particles is significantly larger, okay, and almost it is comparable to the, so here you can see this is unity, so 0.1 to 1. So when size of particles is identical to the length scale of the turbulence, in that range the presence of particles will try to enhance the turbulence. Okay. So while I gave you the second point, we found that presence of particles do modification of turbulence. So how it does modification of turbulence, that is evident from this particular figure. That in smaller sizes it will be decreasing turbulence, but if the size of particle is comparable to the turbulent length scale, then it will be increasing the turbulence. Why does this happen? Let's try to understand. So we define one important parameter which is called as Stokes number, and Stokes number is typically defined as the ratio of particle relaxation time divided by time scale of the flow. Okay, so what was particle relaxation time? MP by 6 pi r mu. So MP by 6 pi r mu was the particle relaxation time for spherical particles, and once it is divided with tau, so tau is my flow time scale. Okay, now when this Stokes number is very small, it is less than 1, what happens? Particle relaxation time is very small in comparison to the flow time scale. Okay, what is particle relaxation time? The time taken by particle to come in equilibrium with the surrounding velocity field. Okay, and tau is flow time scale is the time at which what is happening? The time scale at which velocity of surrounding fluid is changing. Okay, so if the particle relaxation time is very small in comparison to the time scale at which velocity of surrounding fluid changes, what will happen? Particle will be completely following the flow behavior. Is this one clear? Because by the time there will be changes in flow behavior, before that particle can come in equilibrium with the surrounding fluid. So the rate at which the rate at which the velocity of the surrounding fluid is changing in comparison to faster pace particle and can adjust to the surrounding field. So if particle relaxation time is very small than the time scale of the flow, then we will be finding that particle will try to follow each and every flow fluctuation present in the surrounding. Is this one clear? So if particle is trying to follow each and every flow fluctuation, it means if turbulent eddies are present, particle will also try to move with these turbulent eddies. So once particle is moving with the turbulent eddies, what will happen? Of course, for motion of particle across the turbulent eddy has to invest some energy. Okay, surrounding fluid has to provide some energy which is sufficient enough for the particle to rotate. Okay, so it means that when particle is trying to follow the flow, it is consuming some energy of the flow. So once it is consuming the energy flow, it means it is dissipating the turbulent energy. Is this point clear? So that's why for smaller size particles having Stokes number very less than 1, the turbulent intensity decreases. And when the Stokes number is close to 1 or greater than 1, then what will happen? The relaxation time of the particle is more in comparison to that flow fluctuation time. So it means particle is taking more time to adjust to the surrounding flow field in comparison to the time scale at which surrounding flow field is changing. So in this scenario, what will happen? Particle will move slow in comparison to the rate at which surrounding flow fluctuations are taking place. Okay. So particle will actually obstruct the path of the surrounding flow fluctuation. Once it is obstructing the path of the surrounding flow fluctuations, it will try to create additional turbulent eddies by diverting the flow of surrounding fluctuations. So that is the reason when Stokes number is greater than 1, there is enhancement in the turbulence because of the presence of particles. Is this one clear or not? Okay. Because if particle relaxation time is large, it will not move immediately with the fluctuations. So fluctuations will try to bypass over these. Once these are bypassing over these, it will create more chaotic and complex turbulent structures. Is this one clear? Now, whenever the particles do interact with the turbulence, it is not only the length scale, but it also depends upon the amount of particles present. Okay, so let us assume that this particular graph is for d by lt less than 1. So what it means? It means that this is for the particles which are decreasing the turbulence. Okay, so here you can see this is turbulent kinetic energy and this is rate of dissipation. So, and in the abscissa, I am having mass fraction of the particles. So when there is no particle present, say this was my turbulent kinetic energy and rate of dissipation. When I am having 0.1 fraction of particles present, then this is the decrease. And decrease is why? Because the particles are present in length scale such that d by lt is very small than 1. And if I increase the mass fraction of the particles, then changes in the turbulent kinetic energy or reduction in the turbulent kinetic energy will be more. Okay, so more the number of particles present in the flow, more will be decrease in the turbulent kinetic energy. What does this photograph represents? So this is a photograph of a turbulent flow, gaseous medium in which solid particles are suspended. Okay. Now you can see these black colored spots and white colored spots. So what are the white colored spots? These are the particles. And black colored spot is actually gaseous phase. Okay. So ultimately what is happening? You can consider that whenever this flow is happening, then because of the centrifugal action, particles will try to accumulate across the boundaries of the turbulent eddy. So you can assume that the particles are clustered in between the cluster of particle you have presence of turbulence. Okay, and the high shear zones where two turbulent eddies are counter interacting, in these high shear zones you will be finding the collection of the particles. Okay, is this point clear? Now one important point, because everywhere when we are doing this comparison we are writing over here turbulent length scale, and I already told you that turbulent length scale will be of wide spectrum. So typically if you have a channel flow and in this channel of diameter d your turbulent flow is happening, then typically we take turbulent length scale of the order of 0.2 to 0.3 times of diameter of the channel for considering our analysis. Okay, so maybe I'll stop and we'll discuss further in the next class.